Okay. Problem solving. We've done a little bit of problem solving. Now I want to talk about strategies. What is the units digit of 2 to the 1000 power? So, first, does everybody know what a units digit is? Units digit is the same as the ones digit. Ones digit is the one that comes before the hundreds, the tens, and the hundreds and the thousands. So, for example, in the number 147, which one is the ones digit or the units digit? It's 7. Okay, this is just a place value issue. You guys know what place value is? Okay, so the 7 is in the ones place, which is also called the units place. And the 4 is in which place? And the 1 is in which place? That's all this is. Okay. Now, what is the ones digit of 2 to the 1000? Okay, and why do you say that? Okay, so the last digit is, so the last digit becomes 0 when you do what? When you multiply by 1000. Is that what we're doing? No. Right. 2 to the 1000 power means what? 2 times 2 times 2 times 2 da 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 da. Right. So the question is, what's the ones digit going to be? Why do you think 2? Because you start with the 2. Okay. So does that mean 2 to any power is going to give you 2 in the ones place? No? It will be an even number. That's good. Yeah.
It's 2 because if you break it down, like 2 to the 10th power, it's going to be either 2, 4, 8, 16. You know, you're going to go up to like some number.
Okay. You are going to go up to some number. That's true.
And then it's going to like start all over again when you end. Like, you know, you're just doing it over and over and over again. Like, you break it down in 10, like 2 to the 10. Then you add up.
Okay. So let's talk about that. You said it's going to go over and over and over. How could we see whether or not that's true? Just do it. So we have 2 to the first. That's just 2. 2 to the second. That's just 4. 2 to the third. That's 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. Now before I go ahead and write down every single power of 2, we only care about one part of this. Which part do we care about? We only care about the ones digit. So you tell me. Is it?
Yeah, because the next number would be 128. Yeah, the next number would be 128. So like the one digit is going to be 8. And the next number is going to be 256.
Right.
32, I think.
So Terrell, you're right in that you're actually going ahead and figuring out every single power of 2. So that's good, but obviously we're not going to go out to figure out 1,000 powers.
Yeah, but when you find out like 2 to the 10th power, you just multiply by 1,000 or 100 because you already got
Times 100? No.
wait. Yeah, but multiply by 1,000 because since you only went up from 2 to 10 and you need 1,000, you could just multiply the 10th number by 1,000.
But again, remember, we're not multiplying by 1,000, we're raising to the 1,000 power. So everything is always 2 times 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 2. Is it? Is this the same as 2 to the 10 times 2 to the 10 times 2 to the 10? Right. When you multiply in this way, what do you do with the exponents? You add them. Okay. So I appreciate that you're trying to come up with calculation shortcuts. I guess it's a reasonable thing to try given every other thing you've ever learned in a math class. But remember, I warned you at the beginning of this semester that we were going to do things a little differently in this math class, using covering different topics and using different approaches than you've seen before. So that's definitely a good thing to try, but now going to blow up your mind and think about something new. Okay. Back to what we have. What's actually happening here? Yeah. So how can we use what we have here in order to say what's going to happen when we get to 2 to the 1,000 power?
1,000 would be the same digit, the same unit digit as what I still say it would be the same digit as what 10 was, because since 10 is like a something of 1,000.
Okay, so is there a pattern or isn't there a pattern? Okay. Are we all up with that? Okay, so there is a pattern. So notice that the first thing we did was we looked for a pattern. So now we have some vague sense that there is a pattern. The question is, what's that pattern? What's the pattern?
It's going to
2486. Right. Again, remember that what's very nice is that the only thing that we care about is the units digit. So let's go ahead and make sure that's the only thing we're looking at.
The units digit always means the 1.
Units digit is the same as the ones digit.
So then 2 to the 1,000 power, the unit digit would be a 4.
Okay. Why?
Because 2 to the 10th power is going to end up in a 4. And like I said, since 10 is like a, it could be multiplied to get 1,000.
Is that what the pattern is? That whatever happens for 10 happens at 1,000? What's the pattern? The pattern is 2486, 2486. Every 4. Every 4 numbers, what happens? It starts over. So for example, 2 to the 4, the units digit is 6. When is that going to happen again? 2 to the 8. And then when is it going to happen again? 2 to the 12. And then it's going to happen again at 2 to the 16. That's the pattern. So now we just have to go backwards. We have to say, well, we know that we're going to 2 to the 1,000. So which one is that going to be the same as? Is that the same as 2 to the 1, 2 to the 2, 2 to the 3, or 2 to the 4? Now how can you check? How many times does 4 go into 1,000? So how many times does 4 go into 1,000? Yes, 250. So now once you know that, how does that help you? Let me put this another way. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. I'll write it again. This is going to repeat again at 2 to the 5. And where does this one and where does that repeat? The next one. 2 to the 9. And then that repeats again at 2 to the 13. Okay, etc., etc. Next one. Where does this next appear? 2 to the 6, and then 2 to the 10, and then 2 to the 14, etc., etc., etc. The units digit of 8 first happens at 2 to the 3rd, and where does that repeat? 2 to the 7, 2 to the 11, 2 to the 15, etc. I'm putting an arrow there, etc., etc., etc. Okay. 2 to the 4th has a units digit of 6. Where does that repeat? 2 to the 8, 2 to the 12, 2 to the 16, etc., etc., etc. So the only question is, which one of those is going to land you at 2 to the 1,000? Which one is it? Why 2 to the 4? Which one, if you keep, so obviously every time we're going up by 4, the pattern repeats every 4. That's how you know what the next exponent in the line is going to be. So the question is, counting by 4s in which row is going to get you to 1,000? Well, is 1, 5, 9, 13 going to get you to 1,000? Obviously not. Which row? Which row is going to get you to 1,000? Okay. So, first off, we know it's got to be one of the even ones. That's certainly true. But now, is it going to be 2, 10, 14, etc., or is it going to be 4, 8, 12, 16, etc.? And how do you know? There's the keyword, remainder. Absolutely. It's a little harder to see in the 1, 5, 9 sequence, the 2, 6, 10, the 3, 7, 11. But if we look at the 4, 8, 12, that's great. Because not only is that repeating every 4, every number is a multiple of 4. Notice that in order to be in that row, we don't care if it's 4 times 1, 4 times 2, or 4 times 100. But the important thing is that it's a multiple of 4. So when you divide by 4, what's the important information? No remainder. And that's exactly it. So you were right before when, I forget who it was, suggested take 1,000 and divide it by 4. You're right. But the important information isn't that 1,000 divided by 4 is 250. What was the important information? The remainder is 0. Because that tells you which one of these it's going to be as the pattern repeats. If the remainder was 1, which row would we be in? A remainder of 1. We'd be in the row with 1. If we had a remainder of 2, we'd be in the row with 2. If you had a remainder of 3, okay. So we know that going up by 4s is going to take us in the 4th row. That's going to give us all multiples of 4. So that's going to get us to 2 to the 1,000th. Since 1,000 divided by 4 has remainder 0. Okay. So now, for example, what if I said, okay, so I'm sorry, so finally, so what's the answer to this question? What is the units digit of 2 to the 1,000th? It's 6. And there you go. So the answer is 6. So, as a follow-up question, let me see. There we go. What about 2 to the 3,001? What's that units digit going to be? Well, again, what's the pattern? Right. When you divide by, what are we dividing by? We're dividing what by what? 2,000? We need to know what's the pattern? 2486, 2486, 2486. So the pattern repeats how often? Every 4. So if this is going to happen 3,001 times, what do we have to divide by? Okay. And you get exactly what Danielle was saying. So if you like, it's going to go through however many times. It's going to go through 4 a whole bunch of times. But then how many is left over? 1. So we go back into the first number in our pattern, which is 2. Okay. Next one. What is the unit digit of 5 to the 1776? A patriotic power. And how did you get that? Uh-huh. So, someone? What's the pattern? Uh-huh. So, what's it going to be? Right. So the pattern is 5, 5, 5, 5, right. So this is a very friendly one. Because you get 5 to the first is 5, 5 the second is 25. Now of course this doesn't, now I should say this is a pattern. What kind of reasoning are we using here? We're using inductive reasoning. We said we wrote down a bunch of terms and this is the pattern, so we're just going to assume that it always holds. So we should be a little more precise. We should, or a little more complete. We should convince ourselves that it's always going to be 5. So we're pretty sure the answer is 5 because it should always be 5. But let's take a look. If you have any number that ends in 5 and you multiply it by 5, what happens? 5 times 5, you get a 5 there and carry the 2. Now, what do we have to do now? Nothing, because that's all the information that we need. So this shows that in general, for this problem, you're always going to have 5 in the units place, no matter how many powers you take. Now similarly, if you go back to the first problem, to be complete, we should also convince ourselves that this also holds. So I'm just gonna do one of these. So for example, suppose you have, let's go back, star, whatever going on over here, some number ending in 8. And then we multiply it again by 2. What happens? Right. You get 6, carry the 1, and we don't have to do anything else because the only thing that we care about is the units digit. So that's a quick demonstration that no matter what the number is, as long as it ends in 8, and you multiply it by 2, you're going to get something that ends in 6. And what that digit is the only thing we care about. And it's always going to be true. So we went back and we said we had a pattern, but now we've confirmed that that pattern actually is going to work. Always. You dig?
So we have to use 8 to get these numbers.
Well, which number do we have to use? So I showed it for 8. What else should we also really do? Yeah. Show that 2 always goes to 4. Show that after 4 the next number is always 8. We showed that after 8 the next number is always 6, and then what else do we have to show? After 6 the next number is always 2. So if the pattern has 4 pieces, for this to be complete, you really should check all 4 pieces. In our second problem, 5 to the 1776, how many pieces does the pattern have? 1. Easy pattern. Okay. You dig? Alright. So we're now going to talk about what does it mean to do problem solving in general. And one of the, probably the father of problem solving is Polya. His name is George Polya. He was a Hungarian mathematician, and he really helped to advance the whole idea of problem solving as something that you can do again and again. So these sorts of problems, this might seem like I pulled this out of absolutely nowhere. You're like, I've never seen anything like that before, I'll probably never see anything like that again. So the idea behind problem solving is to come up with general strategies that you can apply to any sort of problem, math problem in particular, but also in general. So first of all, he came up with 4 steps. When you are confronted with a problem, what do you do? First, understand the problem. Notice that was something that we had to do because not everyone knew what the units digit was. So we had to get that straight. Next, make a plan. So what was our plan, which I sort of coached us through at least the first time? Yeah. So write out of the first couple of powers, and then try to find the pattern. Step 3, carry out the plan. So in other words, do it. And then step 4, look back and check. So understand the problem usually takes about 5 seconds. Carry out the plan it can be short or it can be long depending upon what your plan is. And then look back and check is usually that 5-second, does my answer work? Yes it does, okay, I'm good. So which is the tough part? To make the plan. Make the plan is basically how do you solve this problem. Okay, but that's what we're going to talk about right now. So the make the plan part has to do with coming up with a strategy of how you're going to solve this problem. So usually what happens in math class is you're told, hey, you have this kind of problem, do these 5 steps. So in essence, the plan is already handed down to you from the textbook or the teacher. You have let's see, you guys have seen quadratic equations. If you see a quadratic equation, what do? Use the quadratic formula. So the make a plan part has almost already been done for you. You just have to recognize what type of previously seen problem this is. So the idea behind problem solving is to say maybe you haven't seen this precise problem before, but just the 3 was changed to a 4. So the idea is that what sorts of general strategies can you use? Well, we just saw one. Look for a pattern. That is a general strategy. You can use look for a pattern in find the units digit problem, but there are lots and lots of other patterns, lots of other problems where you can use that kind of strategy. What are some other common strategies? Trial and error is a common strategy. Everyone's probably used this at one point or another. Okay, so let's give trial and error a go on this kind of problem. So here's a picture. Let's call it a barn. Draw the figure without lifting your pen or retracing any lines. Sorry? Oh, you've done this before? Okay, well. That's another common strategy. Remember how you did it before. Good. So what is everyone doing right now? That's right. Trying and getting it wrong and then trying again. Absolutely. Okay, good. It's hard until you get it, until you get the answer. Once you have the answer, then it's easy. So who's got it? Okay. So Rakib, how many times have you tried so far? 5? Okay. Jose, how many times have you tried so far? Sorry? Once? Okay. Draw faster? Let's see. Elvie, how many times have you tried so far? Once? Do you have it or are you still working? Oh. Okay. And Alicia, how many times have you tried so far? Once? Okay. Do you want the answer or should I let you work it out? What? You can't pick your you can't pick your pen up. Has to be one line. Now you can cross, but you can't go over a line that you've already drawn before. So 6 tries for Daniela. There you go. So right, but you can sort of see that there's only a certain number of possibilities. So if you just keep trying, if you get it wrong, if you just keep trying again, eventually you should get to what has to work out. It also presumes, of course, that if you get it wrong twice, you don't give up. That's important as well. Okay, so I'll let's see. So somebody who got it, how does it go? Yeah. Okay. Go like that.
Then you bring it across the top.
Across.
Cross and make the X. You bring it down like you make an arrow fast, and then you go up, you make the triangle, you go down.
Okay. Proper. I believe there are other ways there are other sequences to go through, but yeah, that'll get it done. There you go. Okay. So presumably everyone figured out or a lot of people figured out the value of trial and error here. Okay, but that's one example. Okay. Next strategy: break it down into cases. Now I should mention that this is we looked at an idea sort of like this, breaking it down into cases before. Actually, not really. So let's just talk about this one. Okay. How many rectangles are there in each picture? So here's the first picture. How many rectangles are in this picture? What are the rectangles? Okay. I don't know what. Okay. So trace the outline of the rectangle in the air so I can see what you mean. Okay, absolutely. So there are rectangles that look like this. What else? There are rectangles that look like this. What else? What other kinds of rectangles are there? Exactly. There are rectangles that look like this. There's only one of them. And what else? And then there are rectangles that look like this. Right. Remember that a square is a rectangle. Okay. So these are all the different kinds of rectangles that there are. So now that we realize that, what should we do? Count up how many of each there are. So of the first kind of rectangle, how many are there? There's 2 of these. Of the second one, how many are there? There's 2. Next one, there's 1. Next one, there's 4. So how many rectangles are there? There's 9. There you go. This one's going to be a little more fun. And by fun, of course, I mean harder, will take longer, and make you sweat more. What's the first thing that we should do? Break it down into cases. And what are the cases going to be for this picture? Okay. Tell me what a rectangle might look like. Okay. So there might be, I need a little more room here. Okay. Let me move this out the way. Okay. So you need all this room, I think. Okay. So first of all, you might have a rectangle that looks like this. What else? You might have a rectangle that looks like this. What else? Vertical or horizontal? Okay, exactly. So you might have a rectangle that looks like this. And so of course you might have a rectangle that looks like this. What else? The one that looks like this. What else? Okay, sure, the full thing. Of course there's only one of those, but you might have a rectangle that looks like this. And what else? Okay, so you might have a rectangle that looks like this. And one of those standing up. You might have one that looks like this. And then of course just the single units. Okay. Have we covered every case? Okay. So now what should we do? Count them up. So the first one, the three long standing, the skinny three, how many of those? There's three. Okay. Next one, how many are there? There's three. The next one, how many are there? Two. Next one, how many are there? Two. Okay. This 2 by 2 rectangle, how many of those are there? Okay. Now this is probably the first kind of tricky one. So does everyone see how many of these that there are? And do you see where they are? There's one of these here, and then where else?
We're in the other corner.
Then there's one here. Then there's one here. And then there's one here. So 4. You dig? Okay. So there's 4 of these. Next one, how many are there? There's 1. Okay. Right. So this guy is also tricky, but at this point we should understand how to count these. First in the corner, and then next to it. Then over here, and then next row, then there's one over here, and then next to it. So just going one by one and shifting it along as is possible, we see that there are 6 of these. Now how many of the next one are there? Obviously also has to be 6, just because the picture is going to be the same but on its side. And then of the last one, obviously there's 9. And now, add them up. And if you add them up, what do you get? What do you get? 36. Oh wait. Isn't it? Okay. Oh, yeah. Okay. So there are 36. So notice that when we first looked at this picture, nobody guessed anywhere nearly as high as 36. So and also notice that if you are not organized in this, where we're using the strategy of breaking it down into cases, imagine how easy it would be to miss one. Imagine if you literally just tried to count rectangle by rectangle without breaking it down into cases. If you tried to say well, there's a rectangle, and there's a rectangle, and oh yeah, there's a rectangle, and then oh yeah, there's a rectangle. If you didn't do it with some sort of organization principle, there's no way you would catch them all. And by the time you got to the 20th one, you'd forget which ones you counted. It would be a big mess. Okay. So that's why breaking it down into cases is often a really powerful strategy. Okay.
No, I was going to say that reminds me of the thing where you're supposed to put the numbers 1 through 9 in that same box without having them to each other.
Yes, and you may or may not be doing that for homework. I don't know. We'll see. Okay. So there are all sorts of little games and puzzles like this that are going to be part of your homework that you're going to be working on. Okay. Any questions so far? Any other questions so far? Okay. So, and something I can't, oh yeah, sorry. Is there a formula? If there is, you're not ready for it. Yeah. If there were to be a way to get a formula for this sort of thing, it would involve some mathematics that we don't know yet. Let's put it that way. Okay. Whoa. Let's see. But here's something that I will show you. So one thing that we did is we broke this down into cases, and then we wrote down all the cases. So we're pretty certain that we got all the cases, but I want to tell you something. We could have written down all the cases in a more organized way. So I want to give you an idea, and I'm not going to show you any fancy mathematics, but I'm going to show you the power of organization. So, what kind of rectangle is this one? How could we describe that rectangle? It's 3 by 1. I'm going to use down. Well, you could call it 1 by 3, but I'm going to call it 3 by 1. I'm going to go down then across. Okay. So this is a 3 by 1 rectangle. What about the next one? It's a 1 by 3 rectangle, etc., etc. So we could organize our information in that way. So the way we've actually written this out is we have 3 by 1, then 1 by 3, then 3 by 2, then 2 by 3, then 2 by 2, then 3 by 3, then 1 by 2, then 2 by 1. So to start off, that sounds like it's not fully organized in terms of being in order. So we could put these in order. Now, what kind of order could we put these in? Yeah. In exactly ascending order. So we could say, for example, start with the smallest. What's the smallest? 1 by 1, and then 1 by 2, and then 1 by 3. Next, 2 by 1, then 2 by 2, and then 2 by 3. Then 3 by 1, 3 by 2, 3 by 3. So already we have a better way of organizing these things.
So you're saying just to write it out numerically? Wouldn't it be
That's the next
easier
step.
if you could see it?
No. Well, yes, it helps to have these pictures. So one thing you could do, for example, is to say, first I'm going to have 1 by 1s, then I'm going to have 1 by 2, then I'm going to have 1 by 3. Next I'm going to have 2 by 1, 2 by 2, and then 2 by 3. Then I'm going to have 3 by 1, 3 by 2, and then 3 by 3. So Stephanie, to answer your question, you can still make the pictures if you want to make the pictures. So you can still use that to help you. So now suppose we had organized our information in this way. Now let's go ahead and fill these things in. How many of the 1 by 1s are there? There's 9. How many of the 1 by 2s? Actually, that's a little small, so let me hear. 9, 6. How many of the 1 by 3s? 3. Next row. How many of the 2 by 1s? 6. How many of the 2 by 2s? How many of the 2 by 3s? Without even counting, what do you think that last row is going to be? 3, 2, 1. And now you just add those numbers up. So, Rakib, you were asking me if there was a way that we could deal with bigger rectangles. Or if we started with, instead of 3 by 3, something bigger like 7 by 7 or something. Well, if we did it the first way, where we just wrote down every single possibility in whatever order we could think of, it would be a huge mess. But what if you do it this way? If you do it this way, you only have to fill in a couple of the numbers. You only have to, you only have to count a couple different cases. Because then after that, what can you do? Exactly. So in this case, we broke it down into cases, but what else did we do? What other strategy did we use? Find the pattern. Exactly. So the more strategies you can use, the more power that you have, and the more you can make a seemingly difficult problem much easier and much more handleable. Okay. All right. So, any other questions? Okay. This is this, right. Oh, let me blow this back down. Okay. So, oops, I have to fix that. All right. So, one thing I want to do right now is remind you of a kind of puzzle. So now I want to show you these puzzles. Alternately, these are called Ken or Math Dokus. So you may remember this. I think I mentioned it once before in class. Okay. So now we're at the point where we're ready to think about doing these problems, but not just as like a fun exercise, but actually talk about the strategy of how do you do a puzzle like this. Okay. So, right. So I have to tell you what the rules are, right? Okay. So this is. So I think a lot of people by this point have seen Sudoku. Not going to go through Sudoku. This one actually involves knowing some math, which is why I love these. So you'll notice that there are different regions that are dark outlined. So for example, One sec. Okay, so let's look at this. Okay, so I can write on it. Okay, so for example, we've got this region right here. So that's darked out, and it's got two squares in it. So what it tells you in the upper corner is that whatever numbers you put in those boxes have to combine to 5 using the operation of addition. Okay, so first of all, what numbers are we allowed to use? Well, how big is this box? How big is the whole box? How big is the entire puzzle? 4 by 4. So what digits are we going to use? 1, 2, 3, and 4. So first of all, you can only use 1 through 4. You can only use each digit once in each row. You can only use each digit once in each column. And the thing I just told you, in each darked out section, the numbers have to combine in the appropriate way. So for example, in what I've circled, whatever numbers you put in there have to add to 5. Now let's compare that with, for example, this section right here. What has to be true there? Exactly. Whatever numbers you put in there has to divide to 2. Okay. So this requires some thought. So let's do this puzzle together. Where's the easiest place to start? The 4. Why? Because it's by itself. Exactly. So when you do a Ken puzzle, or a math doku as they call it, those are the freebies. Those are the gifts. Okay. Next. Yeah. Can you? Why does it have to be 2 and 4? Okay.
You don't know which time to form. They have to put the 2 below the 4 because you can put the 4 in between.
Actually, that's a good. So it varies. Sometimes they make you put them in order. Sometimes they don't. So let's assume that they want it in order. Okay. In other words, is writing 2-4 acceptable? So let's see. Let's pretend that it's not acceptable. So it could only be 4 divided by 2 or 2 divided by 1. But you can't have 4 in the first place. Why not? Because there's already a 4. So this has to be 2 divided by 1. Okay. So
Wait a minute, what are you saying by it can't be in order or it has to be in order? The equation.
So no, yeah. So this is a technical point. I was hoping it wouldn't come up so quickly, but it did. This is the problem with which operations? Division and subtraction. In other words, we wrote 2, 1. So the question is, according to the rules of math doku, would it also be acceptable to write 1, 2? So I think it actually varies from puzzle to puzzle. I think on this site you can't do that. So I'm going to say it has to be in order. So 2, 1 means 2 divided by 1. Can't be the other way around. So let's go with that unless it's a problem. Okay. What next? Okay. So subtract to get 1. So what are the possibilities for that? Okay. Right. So it could be 4 minus 3, 3 minus 2, 2 minus 1. But which ones are possible? Which ones can we eliminate? Right. Can't start with a 4 or 2. And what else? And it can't end with a 1. There's only one possibility left. 3 minus 2. That's it. And there you go. So now looking at the bottom one, has to add to 5. The only thing left in the first column is a 1. So that's got to be a 1. But now you know that has to add up to 5. So you get 4. Top one has to be a 3. There you go. Okay. Now what? Oh, this is... Shoot, this is not going to work. Yeah, okay. This is not going to work. So they're using the flexible rules that it can go either way. So how do I know this is not going to work? Right. Okay. So we have to start from scratch, knowing that for division problems, you can write either 2 divided by 1, or you can write 1, 2. So what we've shown is that assuming that you can only write it in order, for example, in division or in subtraction, notice that we did everything correctly using that rule. So unfortunately, they're not using that rule. No, the 4 is right. Okay. So sorry for that false start. Let's give this another go. Okay. Okay. So let's try 2, 4. Okay. Now what? Okay. Oh, yeah. See? So this is what happens when you guess. When you guess, you have to be prepared to say, I made a guess, but clearly now, the guess can't work. Andy, did you have something or no? Oh, okay. So how far do we need to go back? Okay. This is 1, 2. Then what happens? That won't work either.
I think you gotta change the 4
Okay. All right. Okay. So let's start over. That one was a little tricky. I see how to do it, but I want you guys to work it through yourselves. Well, hopefully, let's find out. Okay. Okay, right. So we always start with the given because that's nice and friendly. Okay. Okay. So, oh, okay. And then there's another given. Okay? Now what? So those are all the givens. Now if you look at, is there anything else that immediately has to be one particular thing. Is for which one? Okay, so we've got 6 by multiplication. So in order to get 6 by multiplication, what do we have to have? Okay, or 2 and 3. So, and I'll just give you some of my secrets. For this, I like to say this is 2 and this is 3, or this is 3 and this is 2. So that's how I make notes for myself of what the possibilities are. Okay. Now what? Well, here's something interesting. We know that in order to multiply to 6, we have to use the 2 and the 3. So what does that tell you? Exactly. For that row, you're left with 1 and 4. So it could be 4 minus 1, or the other way around, 4 minus 1. Okay. What else is possible? What else can we say? Let's see. So let's see. In the next row, we've got getting 2 by subtraction. Is there anything that's automatic there? I don't think so. What about in the next one, getting 2 by division? Okay. Can it be 4 and 2? No, because you already have a 4, so what does it have to be? It's got to be 1 and 2 in some order. We don't know which order yet. So it could be 2 divided by 1, or it could be 2 divided by 1. But as soon as you know that, what else do you know? Exactly. You know that whichever order they go in, you're going to use the 1 and you're going to use the 2. And you've already, in that row, you've already used the 4. So what does that tell you? Has to be a 3 there. Exactly. And now you know that that's 5 by addition, so this has to be a 2. Now as soon as you know that, what else can you fill in? In the bottom left, what do we have? What? How come? Okay. Okay, so right now we're looking at these 2 boxes. What do we know about those 2 boxes? Has to be a 1 and a 4. Actually, for 2 reasons. What's one of the reasons why that has to be a 1 and a 4? Right. On one hand, you've already used the 2 and the 3 in that row, and on the other hand, yes. And on the other hand, in those 2 boxes, what do we know? You've got to have subtract to 3. In a 4x4 puzzle, what's the only way to subtract to 3? 4 and 1. So we've got to use 4 and 1.
In the first row, so you have to put a 1 in the row.
Exactly. The 4 can't go in the first box because there's already a 4 in that column. So that has to be a 1, and then the other one has to be a 4. So now we're getting somewhere. Okay. So does anybody see what next step is possible? Yeah, Jonathan. Where here? You put a 1 there?
We have 1 in the row.
Right. So one thing we know is that in this box, what are the only possibilities?
2 and 3.
2 and 3. Okay. So this is going to be either a 2 or a 3.
I think it's going to be a 2 because it can't be a 3 because if you subtract anything from 3, you're not going to get a 2.
How can you subtract from 3 and get 2?
You can't.
Really?
Unless it's a 4x4 box.
3 minus what gives you 2?
1.
Okay. Okay. So notice that if this were a 3, what would this box have to be? A 1. And if this were a 2, what would this box have to be? Well, how come?
Because we have a 4 in the second.
We've already got a 4 in the second column, so we can't put a 4 there. So if we can't put a 4 there, then we couldn't put a 2 in the initial box. And if you can't put a 2 in the initial box, has to be a 3. What kind of reasoning are you guys using? Deductive. These are things that have to be true. So you'll notice that we're also using logic. If a 2 goes in the first box, then a 4 goes in the second box. But not 4. Can't have a 4 in the second box. Therefore, not 2. And if not 2, therefore 3. All comes round. Okay. So this had to be a, sorry, wrong way. Can't be a 2, so it has to be a 3, and if that's a 3, then this is a 1. Now as soon as that, now we can start filling stuff in.
And if that's a 1, then the one below it is a 2.
Exactly. So first of all, there's now a bunch of stuff we can start to fill in. Where we filled in a 1, this means that this can no longer be a 1. So now this has to be a 2. And as soon as we know that, then the top one has to be a 3. And then this one has to be a 2. Yes. And then in the third row, the only thing left is that this is a 1. But as soon as we know that, in the top this can no longer be a 1. So this has to be a 4. And then the other one has to be a 1. And now, right, this box has to be a 2. And the other one has to be a 4. And we're done. Okay. So that was, I would actually peg that more as a medium difficulty. But that's how you do this sort of puzzle. Now notice that you have to. Now let me just make this comment about Sudoku versus Mathdoku. In Sudoku, you're using the numbers 1 through 9, but it doesn't matter what you use. You could use apples, pumpkins, and pears, because there's no actual calculation going on. It's just it either appears or it doesn't appear. Not so with Mathdoku. With Mathdoku, you're actually doing calculations. So for example, with 6 by multiplication, you have to realize that the only way to get this is 2 times 3. So immediately you know that there can't be a, there can't be a 4 in there, for example. So not only do you have to use logic, you also have to use some arithmetic. But you have to put it all together in, as you can see, a clever and challenging way.